Question 9 says this. Imagine we have two square matrices. We have two square matrices with a condition. So let we have two square matrices with a condition that if you square one, if you square two, and if you square the product of two, it will be identity all the time. It may happen so. I mean, with numbers, let me ask you this. What is a number which is in square delivers 1? Who can answer that question? What's the number which delivers 1 if you square that number? Plus minus 1 if you live in the real numbers, or the whole like a unit or circle if you live in the complex numbers. Good question. What's the matrix which one if you square it that delivers identity? Well, of course, this choice is plus minus identity. They will do, of course. But do we have any other ones? If you don't mind, I'll take you back to the previous question. This matrix, if you multiply it with itself, we just figure out with you, it's just swapping the rows or columns. But if you swap the columns in this matrix, what will happen? It will be identity, isn't it? So this matrix multiplied by itself is the identity. I didn't do a single dot product, and I know the product is identity because I know the structural effect of this matrix. It flips the columns or rows. And that's a very non-trivial example. Square of this matrix is 1, even though it's very far from plus or minus 1. Are you with me? So at least I convince you there are lots of examples of matrices such that if you square them, you come up with 1, with identity matrix. Now back to the question 9. Now we have 3 such matrices. A happen to be so, B happen to be so, and the product AB happen to be so. Now we have to prove that in that case, A and B necessarily will commute. These sort of examples, you have to just manipulate with the properties of the matrices in a smart way, and that is growing this intuition how to manipulate in a smart way. So you can only do that by doing the examples. I'll show you one. It's a very nice one. But the proof itself is just one line of argument. Look at this. What I'm going to do. I'll start with BA. So I start with the right hand side, and I will eventually convert this into the left hand side. Now, identity matrix. Remember, it's the one. It's a basic property, distinguished property of the identity matrix. If you multiply any other one by identity, nothing will change. I'm going to use that property. Here it is. So you see, I introduced 2 identities from the left and from the right. Because of the basic property of the identity, nothing has changed. Now I'm going to replace this IN with A square and this IN with B square. It's given to us, all of them identities. Here's my replacement. So next stage, I'm using 2 identities, A square identity, B square identity. Now, the other property we had for the product is this associativity property. We can multiply matrices, we can put the brackets any way we wish. And I'm going to use this property now. Look at this. First, I'm going to make the observation that A square is simply the product of A with A. BA just changed. B square is the product of B with B. Yes. Now look at this, what happens here. I'm going to put the brackets now around these 2 factors and around these 2 factors. Associativity law allows me to do that. Here it is. But now if I look at these 2 factors, it's one matrix AB times the same matrix AB. It means that it is AB squared. It means it is this thing. But this one is identity. It's now the information which is given to us in question 9. So this is just the identity. And the identity times any matrix, for instance A, is just simply that matrix. Is my AB. We started off with BA, and I took you through justifying each step, making reference to the properties we have for matrix multiplication, or to something we given in the setting of the equation, and I took you down to the left hand side.